to introduce our esteemed guest today. Dr. Petar Velickovic is a staff research scientist at Google DeepMind and an affiliated lecturer at the University of Cambridge. Dr. Velickovic is a leading figure in geometric deep learning, whose work has inspired several work in the area as well as practical applications. On a personal note, as someone involved in AI research in computational biology, Dr. Velickovic's interdisciplinary work has been a consistent inspiration for my work. Today, we will give a talk on decoupling the input graph and the computational graph that is the most important unsolved problem in graph representation learning. Without further ado, let's welcome Dr. Petar Velickovic. Before we start, Petar, would you prefer to take questions during your presentation or afterwards?
I would be happy to take questions during the presentation, although I only have one screen, so I will not be able to know if somebody is asking a question. So if you could interrupt me if it feels like I'm in between slides and there is a question we should address, that would be great.
Okay, sure.
All right. Thanks so much. Can you see my slides? Can you hear me all right?
Yes.
Okay, wonderful, wonderful. These things usually take longer, so we're all good. Let's get started then. So thank you so much for the kind introduction and for inviting me to speak to you all today. I'm very excited about it. My name is Petar Velickovic. I'm a staff researcher at DeepMind and an affiliated lecturer at Cambridge. And as the title implies, I'm going to try to introduce to you what I currently consider to be one of the most important unsolved problems in graph machine learning. So for those of you who are not from graph machine learning, hopefully it gives you an idea of a pretty interesting field that could have ramifications for the remainder of deep learning as well. And for those of you who actually do have some experience with graph machine learning, I hope it inspires you to potentially pursue a problem that you haven't necessarily thought about before. So, of course, I realize that this is a very, very strong claim that I've put right there in the title. I will try my best to justify why it is the way it is. And as mentioned, we will be talking about the computation graph of neural networks, graph neural networks, and so on, and how we might potentially want to decouple it from any input graphs or structures that we have access to. So, before we dive into the specifics of computation graphs, I would just like to set the stage and give a few preliminaries on the machine learning model that we will be using, simply so that if I pull some piece of notation or some piece of equation in the middle of the talk, you don't get too surprised by the specific symbols that I use. So, as kind of hinted at the title stage, we will basically be using graph neural networks as the kind of general architecture that will be our guidance for the remainder of this talk. And I won't go very in depth into what a GNN is. I will just give you kind of an intuitive high-level description where we will call a GNN, for the purposes of this talk, any local function that takes into account features of a node in a graph and the features of all of its immediate neighbors. That's what the XNB is for. And as long as this function processes the features in the neighborhood in a way that's invariant to the permutations of the several neighbors, then overall this is a valid graph neural network, and it maps the features from the input space X to some latent space H. There you can obviously apply this F to every single neighborhood separately, and then stack many layers and do anything else that we typically do in deep learning. Now, of course, I haven't told you how to implement this function F here. I've only told you that there is a constraint on it, that it must be permutation invariant. It might be useful to zoom in to how you actually do it. And you'll see here I've zoomed in on just one node and its immediate neighborhood, and showing you one very, very general way of implementing this rule in a way that it holds the condition of permutation invariance. Specifically, one of the most generic strategies for implementing a graph neural network is the message passing paradigm. And in the message passing paradigm, what we do is every node that is a sender collaborates with the receiver to compute a message vector. So the way you compute it is through the application of a message function, psi. Once all of the messages are computed, you need to combine them together into a single vector. And this is where this aggregation function O+ comes into play. as long as that aggregation function is invariant to the order of the operands. So think, whenever you see an O plus, think this could be a sum, this could be a mean, this could be max, this could be a tension, or anything like this. Anything which doesn't depend on the order in which I present the operands, this is a valid aggregation function. And once you have all of the messages aggregated, you can use them to update the features of the central node, potentially adding a tiny skip connection in there using this update function phi. So this is a very simple equation, but a remarkably general equation. And once you have it, you can use it to basically solve any problem on a graph that you care about. So imagine I give you a graph which is specified by node features, xi, and some adjacency matrix, which specifies the connectivity. How you would traditionally use then a graph neural network on this is you would basically use the neighborhood structure of this graph to inform the neighborhoods for this GNN function I showed you before. And then those GNNs would map our features into some latent space H. And traditionally, at least, they would leave the adjacency matrix intact. And what can you then do with these H's? Well, you can decide if you want to classify individual nodes. You can learn a classifier on each node feature separately, which is shared. If you want to classify entire graphs, you can also do that. However, in this case, you need to be careful that your prediction doesn't depend on the order in which you feed your nodes into the graph classifier. So once again, you need to make advantage of a permutation invariant aggregator to combine all the features of your nodes and then send them to a classifier. And uniquely to graphs, you can also do classification inside the edges, or even predict whether or not certain edges exist, which is why this task is sometimes traditionally known as link prediction. And in this case, once again, you can learn a local classifier, which takes into account the features of the two nodes that are connected with this edge, and potentially any edge features that you might have on top of it. So this picture, it's remarkably concise, but inside it, you see 99.9% of the applications of graph neural networks you see, including some of the famous success stories. They can almost all be expressed as one pathway inside this graph over here. Now, I would love to be able to talk a lot more about GNNs. GNNs are one of my earliest long-term areas of research, and I love talking about them. However, the focus of this talk is obviously not going to be just on GNNs. So if what I've told you in these few slides or what I tell you towards the end of this talk sound very interesting, I do think that there's a lot of resources you can look up if you want to learn more just about the foundations of GNNs. I've given a lot of talks on these topics. Luckily, some of those talks were recorded, and you can actually see some of these talks like this one on my YouTube channel. And it already has about 70,000 views. So I would say the community has battle tested it and confirmed that there's nothing particularly silly in there. And even though the talk is from 2021, it still has a lot of details, which in my opinion hold up pretty well today. So that aside, we're now going to talk about computational graphs. And specifically, what I want to draw to your attention is that inside the GNN equation and everything we discussed so far about GNNs, we've made a potentially quite innocent assumption that we have the best possible ground truth graph. And those are the edges that we use for message passing, and we don't try to use anything else. And we assume that this is always given to us. However, while this claim might sound innocent, and most early stage works in GNNs have made this assumption without ever questioning it, we will actually unpack why it's actually, in most cases, quite a bad idea. And this unpacking will lead us to a dynamic area of machine learning known as graph rewiring. It's, in my opinion, a key emerging area of graph machine learning, and an area that's very important if you want to do proper science with these models. And also just generally studying how different GNN models behave under different computation graphs will reveal really cool connections between state-of-the-art models that we use today and graph neural networks. Spoiler alert, basically everything will turn out to be a case of a GNN. So let me tell you through a computer science example, and afterwards I'll give a more biologically grounded example. Why might it be a really good idea to rewire graphs, even if even if your input graphs might be perfect, as in perfectly represent the problem you're trying to solve? So I will motivate this by a very simple classical computer science problem. Imagine you have a bunch of nodes and edges in a graph, and you need to repeatedly classify whether pairs of nodes are connected in this graph. So does there exist a path between them? I hope it's not too hard to imagine that if I am particularly adversarial to this GNN, I can construct graphs which are basically a collection of really long paths. And when two nodes are connected by a path, the GNN has no choice but to iterate over all of the edges of this path until the two nodes meet in the middle or something like that, at which point you could say that they are connected. And hopefully then it's clear that the time complexity of this particular endeavor is linear in the number of nodes in the graph, right? So how can we deal with this? Well, for those of you who come from computer science, you might already know that there is a solution which actually allows us to do things way faster. And that is, even though our input graph here is perfectly specifying the problem, if we choose to reimagine the edges of our graph in a way that tracks the question we care about the most and doesn't really care about the specific edges used inside the input graph, then we can have a much better chance of efficiently answering these queries. So for those of you who don't know, the data structure in question is called the disjoint set union. And the way it works is for every single connected component in these graph, you will track a tree in a forest, and the root of that tree is the representative for the entire connected component. Now, this abstraction allows me to much more efficiently connect two nodes together. For example, if I want to connect H and D in this particular example, I find their two roots. In this case, those are C and F, and I just make one of those roots become a child of the other. So this gives me a very nice abstraction to talk about all nodes that are in the same component are connected to each other. And then I just need to check if the roots are the same and then decide what to do based on that. And what's really cool about it is that if edges are only ever incrementally added to this graph, I can do a super efficient thing to make all of my future queries really, really fast. So maybe now when I query B and G, whether they're in the same component, that question will require linearly many steps. But then we have this very neat path compression trick where all the nodes you've encountered on your way to the root now can point you directly to the root because it will be optimized for fast retrieval. And now suddenly all the queries you do in the future are going to be super fast for those nodes. And therefore, maybe individual operations might require close to linear time, but amortized over the lifetime of the data structure, you will need a complexity which is the inverse Ackermann function of the size of your graph. And basically, for all astronomically sensible input sizes, this inverse Ackermann function will be less than 5. So we have managed to reduce the complexity for something which is linear to something which is basically constant, just by choosing our edges a little more wisely. And both graphs perfectly represented the problem that we cared about. So it is important, even if you fully trust your input graph, to perhaps think, could I maybe change the edges around a little bit such that I can get answers more efficiently with a model like a GNN? And this actually becomes even more important sometimes in real world networks because some graph structures can induce GNNs to behave pathologically no matter how well you train the GNN. I need to stress this, and we will talk about this more theoretically towards the end of the talk. When I say pathological effects on GNNs, I mean it's an argument over the best case scenario. So if you train the best possible GNN you could over this input data set, if your graph doesn't look good enough to propagate that information properly, that GNN is going to struggle. And there's no amount of clever tricks in the architecture or clever training data that will help you do this better. Okay. And one such pathological issue arises when your graphs that you're dealing with have bottlenecks. And here I've illustrated the bottleneck with a picture and an edge, which is drawn in red, connecting two cliques of fully connected graphs. And I hope you can see kind of intuitively that this red edge is under a lot of pressure for information propagation. Like if you want every single node on the left to be able to meaningfully communicate to every single node on the right, this red edge now has to carry all of that information. There's no other direction in which that information can go. And as a result, you can actually prove this. And Alon and Yahav proved this in their seminal Eichler paper a few years back, that under such circumstances, you need exponentially increasing dimension of features for this red edge to meaningfully carry information as the size of the cliques grows. So this is clearly something that's untenable and something that will make practical deployment of such GNNs basically impossible. So to summarize all of the motivating parts that I've told you at the beginning, just to motivate once again why we're going to need to modify graphs. Even when your graph is perfectly correct, it might not be optimal for the task at hand. So in the path querying example that I told you, both of the graphs, both the disjoint set union data structure and the edges of the input graph, fully correctly encode the information you need about. But one of them requires you to do linearly many GNN layers, whereas the disjoint set union induces in an amortized setting almost constant time layers. So just choosing your edges wisely can make a big difference even if they're correct. And all of our discussion so far was under the assumption that I have a perfect graph given to us, right? But in the real world, perfect graphs or graphs that properly model the relationships of the problem you care about are actually incredibly rare. And I'll just give the standard example that everybody who does graph representation learning comes into contact with at the beginning, because it's the most ubiquitous graph data set, and that is molecular data sets. So molecules are a really good abstraction for analyzing chemical information about certain compounds, but they are realistically only an approximation for the underlying physics. In reality, all pairs of atoms are going to interact in one way or another, not just the ones that you've decided to draw an edge between. And while this might not seem like a big deal in a relatively small molecule, things start to get quite interesting when you consider protein folding, right? So imagine applications like AlphaFold. There, you're working with a polypeptide sequence, which is basically a linear molecule, more or less. But now suddenly this linear molecule folds in three-dimensional space in very interesting ways, such that things that used to be really far away in that linear sequence now end up really close together in three-dimensional space. And they might end up interacting quite a bit, arguably in ways that directly influence the function of this protein. So suddenly, to reason about what this compound is doing, you might need to draw edges between things that, in a chemical sense, aren't actually that close together at all. So this is one very concrete example of an area where even if you have a graph you think is perfect, it's actually only perfect for certain kinds of approximations and not perfect for others. And as mentioned briefly with the bottleneck example, some graphs are just pathologically bad, which means no matter what GNN you train over them, some kinds of computations will be practically, for all intents and purposes, impossible. And up until quite recently, we didn't actually know when this happens. We now have some theoretical work that I hope to share with you by the end of this talk, where we try to quantify exactly where such behaviors would occur. And I would argue also choosing the right computational graph, so the right edges to feed into a GNN equation, might be the key final building block to build basically all of discrete deep learning. Now, this sounds like a really bold claim. Let me try to articulate where it's coming from. Specifically, let's assume that I have an input which is graph structured. Now, I need to stress, when you say you have an input which is graph structured, it's a very, very abstract thing. Basically, everything which you've discretized into a collection of objects, collection of nodes, collection of tokens can be expressed using a graph structure. And this means that when I say you have a graph input, I'm basically saying it's any possible input you can feed into a computer. All right, so it's remarkably general. And now let's imagine I've ran some graph neural network, any neural network that processes that graph, taking into account its graph structure and its node edge or otherwise features, that's the X, and computed some output Y. Now, it is conjectured that I can actually express this GNN always by first doing an appropriate rewiring operation, which changes my input graph in some way, perhaps by adding new nodes and edges and initializing their features, and then running the one-hop GNN rule that I showed you at the beginning. This is what the MPNN is. So the equation which updates node features using a one-hop neighborhood, right? My claim is that, and I've conjectured this in a paper that I published at GTRL last year, that you can express every single GNN in this way by first choosing the right computation graph. That's what the rewiring operation is doing, and then running your usual one-step GNN over that graph that you've inferred. And of course, this argument is far more nuanced and requires you to understand a few more preliminaries than I have time to explain here. But Francesco Di Giovanni, who is one of the top graph rewiring researchers right now, gave a really fantastic talk on this topic at last year's NeurIPS, and the talk is publicly available if you want to listen to it. I think it's a really good source of information for this. And actually, recently, through work of folks from the University of Waterloo, which was published at NeurIPS this year, it was proven that at least for sparse graphs, one-hop message passing neural networks are indeed the optimal architecture. And this proof, at least for sparse graphs, makes it very clear where these gains are coming from and how you can express everything using this model. So if you subscribe to this conjecture, I must stress it's still only a conjecture. If you figure out how to choose the right computation graphs, then you can use the recipe from this slide to build any deep learning model you want for any situation you want. So hopefully, maybe you did not agree with all of the pointers that I raised in previous slides. Maybe you agreed with some of them, maybe not with others, but I do hope that at least some of them resonated with you in some way, and that I've piqued your interest that rewiring an input graph might be a good idea to do. So now let's chat a little bit about how do we do it if we agreed that we need to do it. So let's actually have a more simplifying assumption, which is we don't even have an input graph, and we need to find a way to kind of manipulate it in a right way that we have a graph structure to use. Well, one thing that we can use if we don't have any edges given to us is just to assume that that's how nature intended it and not have any edges whatsoever, like assume there's no relationships between the nodes. Now, what this means in practice is you basically take your collection of nodes and each node lives in its separate subgraph and there's no interactions between them. So if you remember the equation of a GNN that I gave you at the beginning, this is equivalent to saying that the neighborhood of each node is just the node itself, and that's it. And if you then decide to plug this into the GNN equation, you'll basically end up with a pure pointwise MLP function. And under all GNN types and flavors, this boils down to this equation you see over here. And it's actually a remarkably popular machine learning model known as deep sets, in homage of the 2017 NeurIPS paper from Manzel, Zahir, and others that proved a lot of nice theoretical properties of this architecture. So the deep sets architecture is simple, but remarkably powerful. And it basically relies on this assumption that every node is connected separately. Just to itself, and that's it. Well, this is actually the first interesting connection we draw in this work, because using this analysis, we've actually been able to show that deep sets are no more or no less than just graph neural networks operating over the unit graph. Now, of course, if one possibility is to use no edges and just assume lazily that what you're given is what it is, well, I shouldn't say lazily, I should say pessimistically. There is obviously a converse approach where you actually try to use all of the edges. And I call this the lazy approach because it's like, I know my nodes are connected in some way. I'm just not going to try to figure it out myself, and I'll let the network figure out what are the edges that are important. So as you can imagine, in this particular setting, every single node is connected to every other node. So the neighborhood of each node is equal to the set of all nodes. And then you can use this and plug it into your favorite GNN equation. Here, for example, I've used the case of so-called attentional GNNs. And basically, you have this psi function, which tells you the message sent from every single neighbor. You have this a function computing an interaction coefficient between those two nodes. And then you have your usual aggregation and update function. At this point, I would ask the audience, does anybody see this equation and recognize something familiar, or something that, something that's like a popular deep learning model nowadays?
Transformer?
Yes, exactly. So what I've just shown you is indeed a transformer. And this actually highlights our second interesting connection of the day, which is that transformers, one of the current most popular deep learning models, are themselves graph neural networks. If you run a graph neural network over a fully connected graph, where you let all of your tokens interact with other tokens, and you have the attentional flavor, which means you're computing the interaction coefficients as a single scalar and then using them as an aggregation coefficient, then you basically got yourself a transformer. Now, of course, you might wonder, but hang on, transformers were not proposed as graph models. They were proposed as sequential models. Well, it is true. Transformers do have access to sequential information, and they usually inject that information through these positional embeddings in the nodes. But just because you give it a positional embedding doesn't mean that the model is forced to use it or respect it in any way. And in fact, that arguably might be some of the power of the transformer, where it can decide to act like a bag of words somewhere and decide to follow the structure of the words somewhere else. And basically, the actual symmetries enforced by a transformer are just permutation symmetries and nothing else. So once you have the tokens with their position embeddings, you can then permute those tokens however you want, and you'll get identically permuted solutions. And you can imagine this attention mechanism that we saw on the previous slide as basically a system that infers a soft adjacency matrix for your transformer to use. And because they operate over fully connected graphs and using dot product attention, which are all operations using dense matrix products, which are things we can do really well on the hardware of today, like GPUs and TPUs and so on, there's also a common sentiment that that transformers just happen to be the GNNs that are currently winning the hardware lottery. They are the easiest ones to scale on the hardware we have right now, and therefore a lot of the research is going to get piped into them because you can scale them up much more than, say, a sparse message passing update. Now, this connection between graph neural networks and transformers is a very rich and very beautiful one, and I could dedicate an entire talk just on this, but obviously our interest here lays slightly elsewhere with computation graph inference. So if you do want to learn more about this connection, I highly recommend you to check out the blog post in The Gradient that was published by Chaitanya Joshi in 2020. And the title is very easy to find. Transformers are graph neural networks. That is the title. So you can look it up after this talk if you're interested to know more. Chaitanya really goes in depth and compares different parts of the GNN equation with different parts of the transformer equation to ascertain that they actually do have exactly the same computational structure. But of course, these two approaches, assuming no edges and assuming all edges, might be potentially naive approaches which don't require you to think too much about the problem you're solving. And we might be actually interested in something in the middle, something where there is a rewiring that takes place, but it's not a fully connected rewiring and it's not a fully dropped rewiring. So there's two general broad strategies in which you can do this. One strategy is what we call non-parametric rewiring, where you imagine you have an input graph, which maybe respects some aspects of the input you care about, but in some other aspects, like in propagation of information, it's actually quite bad. So what you then do is you have a rewiring operation, which changes the edges in this graph in some way to make it more favorable. And once you have this rewired graph, you can then use it as the graph for your one-hop message passing as before. The key part here is non-parametric. So this rewiring operation is non-parametric. It has no parameters, meaning it depends only on the graph structure that's given, and no parameters take part in inferring these edges. Now, of course, if there is non-parametric, there is also parametric, which in the field we often refer to as latent graph inference. And it's really the same picture as before. The main difference is that now the rewiring operation has some parameters, theta, and it also takes into account the features. So you can basically imagine it as I run a graph neural network over my input graph, no matter how bad it might be, and I use the information from that GraphNet's output to decide which edges to use for a second GNN, right? So these four are the general broad categories in which you can learn these kinds of models. And just for many reasons that plague various types of these approaches, the non-parametric rewiring just happens to live in a particularly sweet spot right now. And just to kind of briefly summarize the argument one might make, deep sets and assuming no edges basically ignores a wealth of information because it's very rare that you have a collection of nodes that don't interact with each other in any way. Having a fully connected graph, which is a very popular approach nowadays, has some other issues with scalability and generalization. And here I don't mean scalability in terms of number of parameters. I mean scalability in terms of context length. So basically, if you do fully connected graphs, you necessarily have a quadratic space complexity, and this is something that at some point you're not going to have the memory to store for many real world graphs, which might have node counts in the millions or higher, right? And also, we will talk about this in more detail later, but when you train a model like this, it is typically hard to get it to generalize outside of the distribution of its training data, because it's sort of specialized itself to graphs of a certain shape. And in those graphs, every single node is a neighbor. So what happens when I give you a bigger graph at test time? If I give you a bigger graph at test time, now suddenly you have a bigger neighborhood you have to deal with, and you've never trained for this neighborhood size. So your aggregation function is not used to disambiguating this many nodes at the same time. And generally what happens is you struggle in those cases. So we'll talk about this in more depth towards the end of the talk. Latent graph inference, while it might be the most general approach with one GNN choosing the edges for another GNN, it also involves a discrete decision in the middle of backprop. So you need to choose edges and you have to somehow find a way to backpropagate through that operation. And that draws with itself a whole host of problems, which many authors have tried to resolve in various papers by doing either straight through estimators or reinforcement learning or something like this to have a parametric rewiring operation which is actually backpropagatable. But all of these issues, as you might imagine, make the problem quite hard to be tracked. So because of this, the non-parametric rewiring just happens to occupy this nice sweet spot right now in all of the methods, because it allows you to use a wealth of theory. So if you have some understanding from like graph theory or related areas of math on which graphs might be particularly good to use compared to the input graph, you can inject that knowledge in a way that you can then prove some theorems about what you have done. And also you can design it to be, it's very efficient, right? Because you just need to do one rewiring operation at the start over your entire data set, and then just use your standard one-hop GNNs as you would otherwise. So for all intents and purposes, for the remainder of this talk, we're going to talk about non-parametric rewiring because it's currently experiencing a bit of a renaissance, both in graph neural networks and in transformer research as well. Whenever you see a long context transformer, which to optimize itself or make it more efficient or anything like that, decides to say, oh, I'm only going to attend over this small subset of my tokens, this is the same as non-parametric rewiring. You are deciding what the computation graph is going to be for your transformer by doing so. So hopefully a lot of the ideas that come from graph machine learning in this context can be leveraged in the natural language domain as well. So I, of course, won't have time to tell you in depth about a lot of these non-parametric rewiring methods, but what I will tell you is that there are three broad strategies in which people have done this in the past, and all three of them might be very useful for various types of problem. So the first one, option A, is what we call diffusion of the graph structure. So by this I mean, you take your input graph, and a good place to search for additional edges might be that graph itself. So what you do is basically use some diffusion operation like personalized PageRank or whatever to try to find additional shortcut edges that might be really good to add based on the diffusion properties of your input graph. And that's basically the idea. It was the graph diffusion convolution paper that Johannes Gasteiger and others published at NeurIPS 2019. And it is quite an elegant and versatile method. It's very simple to use. You just take your input graph, you diffuse it a bit, and then you use some of the extra edges as additional edges. And it's quite easy to use in a variety of situations. It worked remarkably well when it was first released. However, it does carry two big problems. The first problem is that because you're using the input graph to discover the new edges, you're implicitly assuming that your input graph is already good, right? And here, when we say good, we say something like homophilic, which basically means that the edges tend to connect nodes that have the same label, right? So information stays within communities, so to speak. And in that context, if you take a diffusion approach and you raise this adjacency matrix to some power, and then you take additional edges from there, this can then give you even better results. But if your input graph is not good for the task that you're solving or not homophilic, you will end up in a situation where the extra edges you draw just perpetuate the biases in your data set and make it much worse to act forwards. Another problem is because you're slapping on a bunch of new edges in your input graph, this will drastically change the statistics of your graph, and therefore, arguably, what you were able to do with the first graph might not be recognizable in the second graph. So to try to address all of these issues, Jake Topping, Francesco Di Giovanni, and others have tried to come up with a more surgical approach to rewire the input graph. And this paper is another testament to how popular nonparametric rewiring is, because this paper actually won the Best Paper Award at iClear 2022. So it was a really well-recognized paper by the community, this stochastic discrete Ricci flow paper. Now, of course, I won't have enough time in this talk to go into the depth of detail on Ricci flows. I will just say that they find a way to detect which edges are particularly poor for information propagation by imagining the graph as a sort of discretization of a continuous manifold. And inside this manifold, you can hunt for these bottlenecks, like areas that are very small where messages need to travel, by basically areas that have very negative curvature. That's the concept from manifold theory. And they found a way to detect where the most negatively curved edges are using some heuristic approach. And then they just surgically rewire the graph around that edge, right? So they don't bother to expand the graph everywhere. They just find the parts which are hardest for information propagation, and then they just add some new edges to bridge that gap and relieve the pressure on those edges and basically loosen the manifold a little bit. So that's the idea of the stochastic discrete Ricci flow approach. Find an expression that computes something like Ricci curvature, compute it for every single edge in your graph, and then add additional edges carefully around those edges. This now, because it's very surgical, will preserve the statistics of the input graph that you have in terms of average degrees and stuff. But this curvature measure that they've come up with is both local to the graph and potentially quite expensive to compute, as in not very easy to scale on CUDA kernels and things like that. However, it did prove to be a pretty popular approach. Now, option C actually came from our group. So this is work from myself, Mark Lackenby from Oxford, and Andrea Deak from Mila. And basically, in this approach, we're like, okay, so there's been so many problems with trying to take an input graph and then modify it in some way to arrive at a better graph. Because if the input graph is already biased in some way, there's going to be some problems, or it's not going to be very easy to find edges. So we decided actually for this paper to throw out all of those discussions about modifying an input graph. And let's just try to take a graph which is useful for information propagation, right? So it doesn't have to have anything to do with the input graph. It just has to be such that it is a nice sparse graph with manageable degrees of each node that has guaranteed good information propagation properties. And it turns out that these kinds of graphs are really hard to find in mathematics. They're quite elusive, and they have a very common name, which is expander graphs. And only a few constructions are known to mathematics which will give you an expander graph deterministically. And in our paper, we decided to employ one of those approaches using the so-called Cayley graphs of the special linear group that provably have expansion properties. And the idea is you use this to generate a graph which is of similar size to your input graph, but it doesn't have any relationship to the input necessarily. It's just a graph that's excellent at globally propagating information. And then what you can do is you can run one GNN layer over your input graph, one GNN layer over the expander, one GNN layer over the input graph, and so on. The layers over the input graph are there to preserve the input graph topology or any useful information that might be contained inside it. And then the GNN over the expander is designed to globally propagate information in a way that allows the model to most easily leverage that topological information without running into bottlenecks or things like that. So basically addressing any issues that you might have in the input graph through the use of the expander. And you can actually visualize these expander graphs for various sizes. You can see here on the left-hand side what one of them looks like. So every single node has only a degree of 4. It's very sparsely connected. And Yet it's a really good communication network. Every single node can reach any other node in logarithmically many steps. So it's a really efficient computation template. And when you visualize it, I like to say it looks a little bit like the brain. So our brains as well might have specialized themselves to propagate information really, really efficiently, but only each neuron is only connected to a handful of other neurons compared to the size of the entire brain. So I would argue even the biological structures that we come across might themselves be leveraging these kinds of structures, which are quite beautiful. And on the right-hand side, you see for a slightly larger expander graph, what does its local neighborhood look like? And you can see that the 2-hop neighborhood of this red node on the right-hand side already looks quite a bit like a tree. So trees are good in this case because they allow us to exponentially expand our receptive field very quickly. However, you can start to see it's not quite a tree. Already some of the branches of this tree start to close cycles. And this is also very important because if you make it just a tree, you'll get bottlenecks everywhere and it will be very easy to have problems with oversquashing once again. So expanders strike a nice sweet spot between rapid expansion and coverage of the graph while closing sufficiently many cycles that there's a lot of redundancy in the system as well. And what's really cool about the expander angle is that it also explains why transformers are so popular and useful, because fully connected graphs are trivially known to be dense expander graphs, right? So transformers, any transformer network or any fully connected graph network is itself a special case of expander graph propagation. It's just dense expander graph propagation. But here we wanted to see, can you do something with sparse expander graphs that works well? Because sparse graphs will allow you to scale up to much larger sizes of inputs, which fully connected graphs would not. And this approach works remarkably well in practice. So we deployed the expander graph propagation against all of the popular OGB graph classification datasets, which span molecular predictions, molecular interaction prediction, protein-protein interactions, and analysis of code. And we took the standard off-the-shelf state-of-the-art model, the graph isomorphism network. And what we did, as I said, is we changed it such that every second layer in this model operates over the expander graph. I must stress again that in doing so, we have absolutely the same number of learnable parameters as we had in the original architecture, because the GNN has the same message function and update function looks. The only thing that's different is over which edges it's applied. So this is really as apples to apples a comparison as you can get. You get two models with exactly the same number of parameters, but they have different computation graphs. So you can directly compare just the influence of the computation graph and nothing else. And just by doing that, with no extra hyperparameter tuning, we are able to create improvements on most of these 4 data sets, and on none of them is the model worse than the input architecture. So this is a very simple approach. We didn't try to tune it in any way. I can imagine that if we tried to tune it, we would probably get even better results, right? So we completely randomly decided to align the expander graph to the nodes of the input graph. And that's obviously another really hard decision that you need to make. But we've shown that even if you're careless about it, you can still get big performance improvements. So this is something that hopefully is worth considering in the future. So I've given you a quick rundown of three popular ways in which you can do non-parametric rewiring. So taking an input graph structure and expanding it through diffusion, taking an input graph structure and surgically rewiring it through using something like curvatures and Ricci flows, and just ignoring the input graph structure altogether and sampling a graph that you know is good. And then you don't, then you don't worry about it, and you alternate your GNN between the input graph and the generated graph. So now that we've talked about these 3 approaches, and hopefully this has given you some food for thought for future exploration, I would like to close this talk by briefly telling you about our recent theoretical paper with Francesco Di Giovanni, Konstantin Rush, and many others, where we basically wanted to set out to detect when does this bottleneck effect happen? Like when do we get over squashing where one edge has a lot of pressure to store information and so on? So that can we maybe quantify it so that then, people who write these GNN layers or people who decide to write layers for transformers can decide what is the right computational graph structure for you to use in their case. And we have actually been able to define such a property. So this is the equation that is within our paper, and is this over squashing measure. I won't go in depth about this equation, but I will go in depth about the various things that factor inside it. So we have over squashing between 2 nodes in a graph, V and U, And that's using a graph neural network with depth m. So m is the number of layers in your model, and w is the maximal norm of the weights. So in things like the message function, what's the biggest weights you can have in terms of the norm, right? And you get this really nice, complicated but really elegant expression, which tells you how much mixing is allowed between nodes u and v. So we've basically talked this entire talk through the lens of we have two nodes that would really like to communicate with each other, but we cannot easily make it happen in the input graph, so we rewire it to make it easier. So this basically is a measure of how much are two nodes prevented from mixing in a particular graph structure. Once again, I won't go in depth in the different parts of the equation on the right, but I will say that inside this equation, you have both the depth, the maximal norm of the weights, and these S and Q matrices, which are just functions of your input adjacency matrix. So you now have a definition which has a dependence on both the input graph topology via these S and Q matrices, the GNN architecture, which is expressed by the number of layers, and the GNN parameters, which is expressed by the norm of the weights. So you have a very all-encompassing equation which talks about both the shape of the graph and the architecture. Now, what we specifically prove in this paper is that if you want your model to meaningfully fit a particular task that you care about, this over-squashing measure must be smaller than the required mixing between the two nodes that you care about. So this mix quantity is something that you need to know up front or use using the insights you've gathered, that you believe that to solve the task meaningfully, these two nodes must interact this much. That's what mix of u and v tells you. Okay, now armed with that, I think it will be very useful to try to study what this equation gives us in a few special cases. Because I feel like in this case, especially because it's an all-encompassing equation, there are many possible cases where you might want to apply it. So let's start with some simple results just to set the stage and maybe do a bit of a sanity check that our model behaves as expected. So if I were to set w to infinity, which means my weights can grow arbitrarily big, I have infinite capacity in my model, the over-squashing measure, as you would expect, goes to 0. And the meaning of this is if I have large enough weights in my neural network, I can separate anything, right? Literally, the weights can encode the way different features should be split. Now, of course, this doesn't mean you should set your W to infinity, because we still need to optimize these models with gradient descent, and our computers are not exact calculators, they are numerical machines. So you might not want to do this. But it's nice to know that if you do allow yourself infinite capacity, our equation basically says there's going to be no blockages to communication between the two nodes. Of course, there's also the converse of if you set your weights to 0, and this means you only have things like bias vectors or constant inputs or something like that. Now your over-squashing, as you would hopefully expect, goes to infinity, because without weights, without any way to differentiate different messages, all of my messages are constants, and therefore the node features cannot mix at all. And it's mixing that we care about in this context, right? So with the extremes of W, we can see what happens with OSQ, and it's basically as expected. Now let's look at the number of layers. So here is one very popular fact, which our equation verifies. If the number of layers is not big enough to cover the shortest path between the two nodes you care about, and this is what we call in graph machine learning popularly as underreaching, your over-squashing measure will also go to infinity. So what this means is that I cannot mix these two nodes together if my GNN cannot reach one of them from the other, right? And it's a very simple topological fact, but our equation verifies it. So you need to have sufficiently many layers, at least half the shortest path between these two nodes, in order for these two nodes to mix at all, right? And now comes the more interesting. These previous ones were a bit sanity checks. Now come the cases which are a little bit more interesting. So first, let's study the effect of W. So we will fix M, the number of layers, to some sensible quantity, like say the diameter of the graph divided by 2 or something like this, so that all pairs of nodes are allowed to communicate. And we check how big do the weights need to be for the mixing to be useful. And we can actually prove a theorem in this case, which shows that there is indeed a lower bound on how big your weights need to be for that particular deep GNN to allow the right level of mixing. You can see that the mixing constant is present in this lower bound. And it's nice to study this lower bound for certain special cases. So you can see, for example, if your input graph is a tree with branching factor D and depth R, and you set your number of layers to be half the depth so that every leaf can reach the root, you actually end up with this lower bound here, which actually grows with the branching factor of the tree. You have this D+1 factor featured here. And this actually implies that learning on graphs in terms of information propagation is harder than learning on simple paths, right? Because for paths, the lower bound on the weights is going to be smaller. Of course, there might be other problems with learning on paths compared to trees, but certainly learning on non-path graphs can be more tricky than learning on graphs. And you might need stronger weights to deal with that. Another very important result, which relates quite a bit to transformers, is what if our input graph is a complete graph? And we just set the number of layers to 1 because that's what you need theoretically to cover the whole graph. Like every node immediately sees every other node. Here we also derive a lower bound on W, and specifically in this lower bound you get n-1, the number of nodes featuring in the bound. And this is also quite interesting because actually it means that as graphs grow, if they're fully connected, you need bigger and bigger weights to meaningfully separate the neighbors. And this is something we mentioned informally previously, but now we have a theorem that proves it. And this is another reason why transformers might be hard to generalize to larger graphs than the ones you've trained in your training set, because as you get more and more fully connected graphs, more and more of those edges are spurious and useless for the problem you're solving, but the model still has to figure out what are the spurious edges and what are the meaningful edges, right? And, just because you have a lower bound on W doesn't mean you can use it to declare victory. If your W grows too much, that's once again numerically unstable and not particularly useful. So what happens in the opposite direction? If we set the maximum norm of the weights to some particular value, for example, if we do L2 regularization or something, this is a penalty that forces the network to make your W not too big. And then you let the number of layers vary. Well, in that case, your GNN needs to be deep enough to allow that information to mix with those particular weights that you have. And we're actually able, once again, to prove a theorem which derives a lower bound on how many layers you need for that particular W to achieve the right level of mixing. And this equation is a little bit more complicated, but the key thing I want to draw your attention to in that equation is this part over here, highlighted in blue. It uses this tau operation, which is known as the commute time between those two nodes. Now, if you're not familiar with commute time, it is basically the expected number of edges needed in a random walk to start from node U, get to node V, and come back, right? So this is a very tricky operation, especially as your graph becomes more densely connected, because a random walker might decide to walk in the right direction. It might decide to walk in the completely wrong direction as well. And you need to average all of those particular cases together. And we find basically that the depth of the GNN that allows for good mixing must be at least on the order of the commute time. And this is quite telling because it's not as simple of a condition as the shortest path condition that we had for underreaching, because for many graphs, you can build such inputs where the commute time between two nodes is sometimes cubic in the number of the nodes. So it's much worse than shortest path distance. And this means that over those graphs, to get meaningful mixing between those nodes, you need a GNN that has n to the cubed layers, potentially, to theoretically make them mix in a proper way. And this is, for all intents and purposes, a practical impossibility result for many graphs of interest. So it's not just enough to have as many layers as your shortest paths. You need to carefully choose the number of layers in a way that depends on the nuances of the graph topology. And expander graphs, once again, come into play here because they are known to be graphs with really favorable commute times. And this kind of approach justifies our expander graph propagation method. So just to briefly conclude and hopefully have some space for questions if there are any. In most cases, we don't have fully correct graphs to give our GNNs. And even when we do, we might benefit from having specialized graphs for the task that we're solving. And not all graphs are made equal in terms of how good they are for message passing. If you have graphs with high commute times, they're going to be detrimental to mixing of information, no matter how well you train your GNN. Remember our definition, both factors, the topology, and the graph neural network architecture. And rewiring might be the key sufficient missing piece to explain any discrete deep learning architecture you care about. So if you find a way to choose the right computation graph, no matter how hard of a problem it might be, it is a key unsolved problem in deep learning. And currently, this non-parametric diffusion hits the sweet spot between tractability and elegance, because you can diffuse the graph, rewire it, use an expander graph in a way that's theoretically motivated, and also can be made scalable if you choose sparse graphs in a way that just processes your data set at the beginning. And now we have this formula for oversquashing, which hopefully you can use to assess when certain graphs might be better than others numerically, rather than just by looking at them and sort of intuitively saying so. And on that note, this was my last slide. Thanks again to the organizers for inviting me to speak to you all today. And many thanks to the co-authors who worked on the various papers with me, Michael, Andrea, Francesco, Mark, Sid, and Konstantin. If you have any questions, I'm happy to take them. And also, after the talk is over, you can reach out to me via email or via my various social networks for follow-up discussions. Thank you so much.
Thank you, Petar.
Thank you, Petar. So let's take question if someone have any.
Okay, I can go on then. Hi, Peter. Thank you for the seminar. It was great. My question is related to the graph rewiring. We are just, I think, as far as I understand, we are just rewiring once. Does the iterative rewiring improve the performance at the end?
That's a great question. Yes, all of the approaches I've mentioned here have been just single-step rewirings at the beginning. I think it was mostly to stress just how much we don't understand about this field at the time, when we're still getting so many gains just from choosing a rewired graph at the beginning. I fully agree with you that you might want to rewire a graph multiple times. And one of the earliest graph rewiring papers, the DGCNN, actually does this. So at every single layer, it rewires using the proximity of the features in Euclidean space. And it has lots of good properties. Let's say you want to classify a point cloud for what object it is. If you have nodes on the legs of a chair, if you just propagate using the Euclidean distance of the input nodes, you'll have each node being aware that it's inside a leg, but there's many objects that have legs. Whereas if you rewire first using the Euclidean distance of the coordinates and then using the Euclidean distance of the features that you get after running the GNN, suddenly, the nodes at bottoms of the four legs are very symmetrical to each other usually. So now the rewiring method might connect them. And now each node, even after a few layers, knows that there are four legs. And now this tells you much more clearly that you're looking at a chair, right? So yes, approaches like DGCNN have tried this. The problem is, the reason why they're not getting as much attention right now is just because we're extracting so much signal from predetermined graphs. And also it's getting quite popular in transformers as well, with these sliding window attentions and things like that, we haven't yet kind of milked the basic rewiring for all it's worth. But yes, iterative rewiring is definitely important, especially if you want to combine features at various scales. So definitely.
Thank you. My second question is, can we, for example, for biological or chemical representation, we have no control over our graph representation, but let's say I'm building a relationship app, Facebook or Instagram, but we have relation graphs. Can I force my graph to have some sort of structures, which is pretty close to this rewiring or optimal configuration before doing any sort of rewiring at the end? Because our graph might get large, too big, which makes rewiring quite infeasible at times.
So I might not have heard the question too well, but what I understand is it relates to rewiring inside biological graphs and how to incorporate additional information, or what happens when they get too large. Was this the question, or?
No, my question is, since we can't have control over biological representation, rewiring is logical, but if they have a relationship graph in a social network, since we are building the graph, can we have some sort of heuristics to graph to have this structure of optimal configuration beforehand?
Yeah, I see. So as I said, even in biological kind of models like chemicals or something like this, your input graph, even though there is a clear heuristical way to approach it, like, using the chemical graph structure, even that might not be the perfect structure if you look at the physics of the underlying molecule. So even in those cases, you might benefit from a rewiring, even if your input graph is perfect in terms of the local chemistry. Proteins are a pretty good example of this. In social networks, of course, the actual social network you're looking at is not the actual social network of people in real life, because not everybody is friends with each other on a social network, and not everybody who knows each other in real life is friends on a social network, and vice versa, right? So there, obviously, you have a lot more space to how you choose to rewire things, and rewiring can also be seen as connected to a recommender system, right? Like, you can use some of the outcomes of the most salient edges to recommend who should you be friends with next, or something like that, or who you might have missed. So definitely.
Any other questions?
Anyone doesn't have? I think I have one more for people.
Let's see if there is any other, Ömer. Maybe you already asked too, so I guess there is none. So go ahead.
Like, since you said that we are rewiring graph for optimal performance, but can we some sort of prevent graph, such as prevent transformers, in a way that we can achieve more with them?
So I think your microphone is a bit poorly calibrated. Could you write your question in the chat? Because I really cannot properly make out the words you're saying.
Yeah, Ömer, while you're writing it, maybe I can ask a question, Peter. So in computer vision, we use graph neural networks a lot for tracking, right? And when you track people, there are certain priors. For example, people walking in a line. Is there any way to incorporate such priors, like as an additional structure, or things like when two people walk together? This is like one of the biggest errors, because there are occlusions when people walk together, and there is this ID switching between two person and so on. Can we incorporate such priors to, for example, when we sample the graph in your approach?
Yeah, so you can definitely, in generally speaking, it's a very generic question. I would say you can definitely incorporate any prior you want into how you sample the method. In fact, if you look at, okay, I'll give a brutal example, but like, you've seen that commute times can be very indicative of mixing between the two different nodes. So let's imagine a hypothetical situation where you know that your label just depends on these two nodes and nothing else. What is the optimal graph for that? It's a graph with exactly one edge that connects these two nodes, right? That has optimal commute time of 2 for those two nodes, because you just take one edge and you take one edge back, and that's the average, right? As the graph gets denser and denser, it's harder and harder for exactly those two nodes to match to each other. And transformers, for example, now have to sift through n irrelevant messages to just find the one that is relevant. So what this means in a graph theoretical setting is a motif, right? So there's a prior assumption that these two nodes are really important to talk to each other, and you bake that assumption into the specific commute times around that region of the graph. So yes, you can use the language that we just talked about to express some prior over which pairs of nodes or which collections of nodes should communicate really, really well. And then you kind of build a local expander graph structure around those nodes to make sure that communication is as efficient as possible. By the way, what I just described to you is basically original research. Nobody has tried to do this yet, but it is a natural corollary of what we have described. So yeah, I'm using just direct fallouts from our method. I'm not talking about anything more in depth, but you can generalize this to say any kind of graph motif you care about, you can bake it into the generative process for the graph you're using.
Thanks. And Ömer wrote his question. Can we do rewiring for the transformer, which at the end can be seen as pruning or quantization after we pre-train the model?
Okay, interesting. So okay, first, you can definitely do rewiring for the transformer. A lot of people are doing it now, especially when you reach 100,000 and larger context lengths, because you cannot do 100,000 squared. It just doesn't fit. So what you need to do is you need to carefully choose which tokens talk to which other tokens. either using some sliding windows or using some expansion-like graphs or randomly dropped nodes or something like this. So rewiring in transformers is already done quite a bit. It's just maybe they don't recognize as much the connection between the two fields. Can you see it as pruning or quantization? I mean, you can definitely use the trained models, graphs, because softmax tends to specialize quite quickly. It's a very brittle function, actually. You can use the graphs obtained by the attention heads as a sort of, pruned graph structure. However, I think there's still a generalization issue at play here, because these attention coefficients were learned when you were dealing with problems of a particular size. And now if at test time I want to deploy the system to larger and larger problems, you haven't necessarily trained your attention mechanism to deal with those bigger settings. And this is part of the reason why, if you, for example, take any state-of-the-art language model and you ask it to even do something simple like sort a list or concatenate two lists together, once you make those lists big enough and you don't allow tool use or code interpretation, that model will eventually collapse, because the attention mechanisms it learned haven't learned a general rule. They depend on some hacking of inputs of a certain size. So yeah, I hope this answers your question.
Thanks a lot, Peter. Thanks everyone who attend. We are already 5 minutes over the time. This was a great talk, and Moaz is here. We are actually in this room. There are more people here. We watch it together. So we thank you a lot for accepting our invitation.
No worries. Thanks so much for inviting me. It's an honor.
Yeah.
Thank you.
Bye. Bye, everyone.
Thank you.